How does an AI know that happy and joyful mean almost the same thing, but happy and stapler don't? It doesn't read a dictionary. It turns every word into a point on a vast map of meaning and simply looks at what's nearby. That map is built from embeddings, and they quietly power search, recommendations, and the RAG we keep mentioning. Let's go deep. An embedding takes any object, a word, a whole sentence, an image, a product, and turns it into a vector, a point in space, placed so that meaning becomes geometry. Today we'll see three things: how that map is built, the genuinely beautiful structure hidden inside it, and vector search, how you find the nearest meaning among billions of points in milliseconds. Meaning as coordinates. Start with the core idea. An embedding is a set of coordinates for meaning. Picture a giant map where every word has a location. The model places them so that similar meanings sit close together and unrelated ones sit far apart. Cat lands right next to kitten, and a short hop from dog. Democracy is off in a completely different region. The position is the meaning. And it isn't just two dimensions. Real embeddings have hundreds, even thousands of them. You can't picture a 768-dimensional space. But the rule is identical. Nearby means similar. We flatten it down to a 2D map just to look at it. But the model works in that vast high-dimensional space, where there's room for every shade of meaning to have its very own direction. Why is this so powerful? Because it converts a fuzzy, human question, how similar in meaning are these two things, into a precise, mathematical one, how close are these 2 points? And that a computer can answer instantly. Meaning becomes distance. That single move is the foundation under modern search and recommendation. How they're learned. So who decides the coordinates? Not a human. That would be hopeless. A model learns them from mountains of text using one deceptively deep principle. You shall know a word by the company it keeps. Words that show up in similar contexts must, somehow, mean similar things. Here's the trick in action. The model plays a simple game across the whole internet. Predict a word from its neighbors, or its neighbors from the word. And to get good at that game, it is forced to give words that appear in similar surroundings, like coffee and tea, which both get poured, sipped, and brewed, similar vectors. Do that billions of times, and a rich map of meaning crystallizes, all on its own. And the very same idea generalizes far beyond words. Train a model to tell which caption goes with which photo, and it learns to embed images and text into one shared space. Show it what users click, and it embeds products and people so that things you might like are simply nearby points. Whatever the data, the recipe is identical. Similar things, placed near each other. The hidden geometry. Now the part that genuinely feels like magic. In a good embedding space, directions carry meaning, not just positions, directions. Take the vector for king, subtract man, and add woman, and you land almost exactly on queen. The model was never taught that relationship. It simply fell out of the geometry. What's happening is that abstract concepts have become consistent directions in space. There's a gender direction, step along it, and you turn king into queen, actor into actress. There's a plural direction, a past tense direction, even a rough capital city direction that carries Paris to France the same way it carries Tokyo to Japan. Meaning isn't only where you are. It's also which way you move. This is why embeddings are so much richer than a simple lookup table. They don't just store that two things are similar. They encode how they relate. As geometry you can literally do arithmetic with. And that structure was discovered, not designed. It's the very same structure those attention layers exploit, deep inside every transformer. Measuring similarity. To actually use this map, you need to measure closeness. And the standard tool isn't straight line distance, it's cosine similarity, which looks at the angle between two vectors and ignores their length. Two vectors pointing the same way are similar, no matter how long either one is. It's the direction that carries the meaning. And you've already met the machinery. Cosine similarity is essentially a normalized dot product, that one operation from before. Same direction, value near 1. Very similar. Perpendicular, near 0. Unrelated, opposite. Near -1, so find me things that mean something similar becomes find the vectors with the highest cosine similarity to mine. Now we just have to find them. Fast. Vector search at scale. Here's the real engineering challenge. You have a query, its embedding, and a database of millions or even billions of vectors. You want the closest few. The obvious way is brute force. Compare your query against every single vector and keep the nearest. Correct, simple, and hopelessly slow at scale. Billions of comparisons per query just won't fly. So we cheat. Brilliantly. Instead of the exact nearest neighbors, we settle for the approximate nearest neighbors, ANN, and in exchange, we get an enormous speedup. The trick is to build a clever index ahead of time that organizes all the vectors. So a query can leap straight to the right neighborhood without ever touching most of the data. The most popular index, called HNSW, builds a layered graph of the vectors. Think of a subway map with express lines up top and local stops below. A search drops in at the top, takes a few express hops to roughly the right area, then walks the local connections down to the closest points. Billions of vectors, searched in a millisecond or two, by looking at almost none of them. And that capability, store embeddings, and find nearest neighbors fast, is exactly what a vector database is for. It's the storage and retrieval engine sitting underneath modern AI search. You hand it a query vector, and it hands you back the most similar items in real time at massive scale. What it all powers. Now the payoff, because this one mechanism is genuinely everywhere. Semantic search. Instead of matching keywords, you embed the query and the documents, and return the closest in meaning. So a search for how to fix a flat finds a document titled Repairing a Punctured Tire, with not a single word in common. It understands intent, not just spelling. Recommendations. Embed users and items into the same space, and what might you like becomes simply what's nearby. Embed your listening history, find the closest songs you haven't heard yet. And of course RAG. That whole retrieval step is a vector search. Embed the question, find the nearest chunks of your documents, and feed them to the model. Plus all the quieter wins. Clustering similar items together, spotting near duplicates, and detecting anomalies as the points that sit far from every cluster. Once your data lives in an embedding space, a huge range of different problems collapses into one familiar shape. Just find the nearby points, where it's heading. And in 2026, these spaces are going universal. A single model now embeds text, images, and audio into one shared space. So a photo and the sentence that describes it land in the very same spot. You can search images with words or audio with a picture. The embedding is quietly becoming the universal interface between every kind of data and the models that reason over it. So step back, and the pipeline is beautifully simple. Take anything, a word, an image, a question. Run it through an embedding model to get a vector. Drop that vector into a space full of others. And to use it, just find the nearest neighbors. Embed, store, search. That is the entire machine behind a startling amount of modern AI. So here's the whole picture. An embedding turns meaning into a location on a map. A model learns that map from the company things keep, and the map hides a deep geometry, where directions are concepts. Cosine similarity measures closeness. Approximate nearest neighbor search finds it among billions in milliseconds, and a vector database makes it all real-time. Search, recommendations, RAG. Every one of them is the same quiet trick. Turn things into points and find what's nearby. So the next time a search just gets what you meant. or a recommendation feels a little eerily, right? You'll know the secret underneath it. Somewhere, your meaning became a point on a map, and the machine simply found its nearest neighbors. Subscribe for more such intuitive videos.